At the centre of many galaxies, there is a darkness so massive it can bend stars into hidden orbits. But what happens when that darkness is missing? A galaxy may still turn, still glow, still carry billions of suns through space, with no black hole at its heart. That possibility is quiet, strange, and deeply revealing, because it asks whether black holes are cosmic necessities or only common passengers in the long history of galactic growth. Welcome to Calm Space Science. If this kind of calm cosmic mystery helps you relax, please like the video, subscribe, and share it with someone who enjoys drifting through science at a slower pace. Thank you for spending your time here. It would be lovely to know what time it is where you're watching or listening from, and where in the world this video has found you. So leave a comment below. Now, let the journey begin. A galaxy can seem, at first, like a thing with a hidden engine. It turns slowly, carrying stars, gas, dust, old clusters, newborn suns, and long rivers of invisible matter around a common centre. In many of the largest galaxies, that centre contains a black hole so massive that it feels almost natural to think of it as the heart of the whole system. Bright active galaxies announce their central black holes across billions of light years. As gas falls inward and releases more energy than entire populations of stars. Yet a quiet question remains beneath this familiar picture. Could a galaxy exist without a black hole at all? Not merely with a sleeping one, not merely with one too small or too dim to notice, but with no central black hole waiting in the dark. The question sounds simple, but it opens a deeper uncertainty about what a galaxy truly is. A galaxy is not defined by its black hole. It is a gravitational system, a bound collection of stars and gas embedded in a larger halo of dark matter. Its shape can be a spiral disk, a smooth elliptical swarm, an irregular scatter of young blue stars, or a faint dwarf barely brighter than the darkness around it. In all of these forms, the galaxy is held together by gravity spread across enormous distances. The central black hole, when present, may be dense beyond ordinary imagination, but it occupies a tiny region compared with the galaxy itself. Its direct pull dominates only close to the centre. Farther out, the stars do not orbit the black hole in the same way planets orbit the sun. They move within the combined gravity of the stellar disk, the central bulge, the gas clouds, the dark matter halo, and the long memory of past mergers. This means that removing the black hole from the middle does not automatically dissolve the galaxy. The stars would not simply drift away. The spiral arms would not instantly uncoil. The outer halo would not lose its grip. The black hole is powerful, but it is not the whole architecture. This is the first quiet clue that a black hole-free galaxy is not forbidden by gravity. The universe does not require a dark central point in order to gather stars into a galaxy. It requires mass, cooling gas, density fluctuations, and time. In the early universe, slightly denser regions pull in more matter than their surroundings. Dark matter gathers first, forming broad invisible wells. Gas falls into those wells, heats, cools, fragments, and eventually forms stars. Over time, smaller systems merge into larger ones. Disks settle, bulges grow, stellar populations age. Black holes may form along the way. But the first outline of a galaxy can appear before any central giant has become obvious. The black hole may be a passenger that grows with the galaxy, or a consequence of the same conditions that build the galaxy, rather than the original cause of the galaxy itself. Still, the universe rarely follows only the simplest path. Observations show that many large galaxies do seem to contain central supermassive black holes. Their masses often relate, in a broad and imperfect way, to the masses of their host galaxy bulges. This connection hints that black holes and galaxies influence each other over cosmic time. When gas feeds a black hole, the region near the event horizon can blaze as an active galactic nucleus. The energy released can heat nearby gas, drive winds, and limit future star formation. In this way, a central black hole can shape the later life of a galaxy, especially a massive one. It can act less like a heart that pumps the galaxy into existence, and more like a regulator, sometimes quiet, sometimes violent, sometimes preventing the galaxy from making too many new stars too quickly. But a regulator is not the same as a requirement. A galaxy can gather without a central black hole, though a black hole may later alter its rhythm. The difficulty is that absence is hard to prove in astronomy. A black hole does not shine by itself. It is seen through its effects. If gas falls into it, the gas may glow. If stars pass close to it, their speeds may reveal an unseen mass. But when a black hole is small, unfed, or surrounded by too little matter to disturb, it becomes almost perfectly quiet. It may sit at the center of a galaxy like a sealed well in a silent courtyard, present but unannounced. This makes the question especially delicate. A galaxy with no detected black hole is not automatically a galaxy with no black hole. It may simply be a galaxy whose black hole has fallen below the reach of current instruments. The difference between absence and silence becomes one of the central puzzles. There are galaxies where the evidence for a central black hole is strong, and there are galaxies where it is weak, ambiguous, or missing. The Milky Way provides a clear case because stars near its center swing around an invisible compact mass with extraordinary speed. In more distant galaxies, such detailed tracking is much harder. Gas can be stirred by star formation, bright activity can fade, dust can hide the center, a black hole can be too light to measure against the surrounding stars. So the universe may contain galaxies whose centers are truly empty of black holes, but separating them from galaxies with merely undetectable black holes is like trying to distinguish a silent room from an abandoned one by listening through a wall. The most likely places to find such a galaxy are not the grand spirals and giant ellipticals, but the smallest and faintest systems. Dwarf galaxies are important because they preserve clues from early cosmic history. Some contain central black holes, some appear not to. Their shallow gravity and turbulent pasts make them vulnerable to disruption. A burst of star formation can push gas outward. A close encounter with a larger galaxy can strip away material. A merger between small galaxies can disturb the center. If a black hole forms there, it may remain small, or it may be pushed away, or it may never form at all. In these low-mass galaxies, the connection between galaxy and black hole becomes less certain. The rule that seems common among large galaxies begins to loosen. A black hole may be frequent, but not inevitable. The question also reaches into the origin of black holes themselves. Stellar mass black holes form when massive stars collapse, but supermassive black holes require another story. They may begin as remnants of the first stars, as direct collapses of a large gas clouds, or as the outcome of crowded clusters where smaller objects sink together. Each path has requirements. Each path depends on local history. If a young galaxy does not meet those conditions, or if its early black hole seed is lost, starved, or never born, then a galaxy without a central black hole becomes a natural possibility. The center of such a galaxy would not be a dramatic void. It would simply be a region where stars and gas respond to the broader gravitational field rather than to a compact monster at the core. There may be a dense star cluster instead. There may be old red stars crossing in slow, tangled paths. There may be gas clouds forming new stars, or almost no gas at all. The galaxy could continue moving through the cosmic web, orbiting a larger neighbor, merging, fading, or forming stars for billions of years. Nothing about ordinary galactic gravity demands that an event horizon sit at the middle. The black hole, when present, is an extreme feature, not the definition of the system, and yet the absence would matter. A confirmed galaxy without a black hole would become an important sign that the link between galaxies and black holes is not universal. It would help reveal whether central black holes are born with galaxies, added later, or only common in galaxies that reach certain masses and histories. It would sharpen the boundary between necessity and habit. A galaxy without a black hole would be not a contradiction, but a clue. It would show that the darkness at a galaxy's centre may be powerful, influential, and ancient, while still not being required for the galaxy to exist. In that possibility, the mystery becomes gentler and stranger. The missing centre is not empty of meaning. It is a reminder that galaxies are not built around one object alone. They are built from distributed gravity, long histories, hidden matter, cooling gas, and countless stars moving together through time. The black hole may be there, silent and patient, or it may not be there at all. For now, the difference remains one of the quietest questions in space, held inside the faint centres of galaxies that do not yet reveal whether they are hiding a darkness, or whether the darkness was never born. The centre of a galaxy feels important because the eye is drawn there, toward the bright knot, the crowded bulge, the place where orbits tighten and stellar light thickens into a haze. Yet the deeper structure of a galaxy is not built like a solar system. It does not place nearly all its mass in one central object, while smaller bodies circle obediently around it. A galaxy is more like a vast weather system made of gravity, where every part helps shape the motion of every other part, and where the greatest mass may not shine at all. The stars near the centre can be influenced strongly by a central black hole if one is present, but the galaxy as a whole is governed by a much wider field. That field comes from stars, gas, dust, stellar remnants, and above all from dark matter, the unseen substance whose gravity appears to surround galaxies in enormous halos. In this broader view, the black hole becomes a compact and sometimes dramatic resident. Not the pillar that holds the entire island together. The difference matters because it changes the question. A galaxy without a black hole would not be a galaxy without gravity. It would still have the distributed pull of billions of stars, or in a dwarf galaxy perhaps millions of stars, along with cold gas, old clusters, and a dark matter halo extending far beyond the visible edge. These ingredients can bind the system even if the centre contains no event horizon. The outer stars do not need a central black hole to keep their paths. Many stars in a galaxy orbit so far from the centre that the direct gravity of a central black hole is almost negligible compared with the gravity of all the matter around them. Their motion is not like a planet circling a single sun. It is more like a leaf carried through a broad, slow current, responding to the shape of the whole river rather than to one stone beneath the surface. This is why galaxies remain coherent across distances that seem almost impossible. A spiral galaxy may span tens of thousands of light years, while the region where a supermassive black hole dominates stellar motion may be much smaller by comparison. Close to the black hole, stars can race in tight, sharply curved paths. Farther away, the black hole becomes only one contribution to the total mass. Beyond the central bulge, the disk and halo take over. The stars there feel the combined gravity of everything interior to their orbits, plus the shaping influence of surrounding dark matter. The galaxy is not held together by a single anchor. It is held together by a shared gravitational landscape. Dark matter is the hidden architecture in this landscape. It does not emit light, does not form glowing clouds, and does not announce itself through familiar chemistry. But its gravitational effect is written into the motion of galaxies, In many spiral galaxies, stars far from the centre move faster than visible matter alone would predict. If only the luminous disk and bulge were present, those outer stars should orbit more slowly. Instead, their speed suggests that each galaxy sits inside a much larger mass halo, one that stretches outward into darkness. This dark halo is often the dominant mass component of the galaxy, especially at large distances from the centre. It is not a point, it is a surrounding well. It gives the galaxy a broad gravitational envelope, a deep basin in which ordinary matter can gather, cool, and form stars. Without this halo, many galaxies would be difficult to explain. Without a central black hole, their large-scale existence remains far easier to imagine. Gas adds another layer to the structure. In young galaxies and star-forming disks, gas cools, collapses, fragments, and feeds the birth of new stellar populations. It can fall inward along bars and spiral arms, or be pushed outward by supernova and stellar winds. A central black hole can affect this gas when it is actively feeding, but ordinary stars also shape it constantly. Whole regions of a galaxy can regulate themselves through cycles of collapse, heating, and dispersal without requiring a black hole at the centre. This distributed nature of galactic gravity explains why a missing black hole would be subtle. If the black hole in a large galaxy simply vanished in an ideal thought experiment, the stars closest to it would notice most. Their orbits would change. Gas in the innermost region would settle differently. Any active nucleus would fade. But the galaxy's outskirts would barely respond at first, because the missing mass would be tiny compared with the mass of the whole system. Even a supermassive black hole containing millions or billions of solar masses can still represent only a small fraction of a massive galaxy. In some cases, it is deeply important for the centre and for the history of feedback, yet not massive enough to dominate the entire galactic body. The galaxy would lose a central extreme, not its gravitational foundation. The same distinction appears in the way galaxies rotate. Rotation curves, the measurements of orbital speed at different distances from the centre, reveal how mass is arranged. In a simple system dominated by one central object, speed should fall with distance in a predictable way. Galaxies do not usually behave like that. Their outer regions often rotate as though much more mass is spread through a halo. This is one of the central clues that dark matter matters more to the overall galactic structure than any central black hole. It is also a reminder that visible shape can mislead. The glowing centre may look like the source of order, but the invisible halo may be the deeper reason the galaxy holds together. The bright centre is only the visible crest of a larger gravitational sea. This is where the idea of a galaxy without a black hole becomes less strange. If galaxies are assembled inside dark matter halos, if stars and gas create much of the visible structure, and if central black holes influence mainly the inner regions unless they become active, then black holes are not required in the same way dark matter halos appear to be required. They may be common outcomes of galaxy formation, especially in galaxies that grow massive central bulges. They may be almost unavoidable in certain environments, where gas repeatedly flows inward and dense stellar systems encourage black hole seeds to grow. But common is not the same as universal. A galaxy may often contain a black hole, but its identity is larger than the hidden object that may or may not sit at its core. The mystery therefore shifts from whether a galaxy can be gravitationally possible without a black hole to whether the universe usually gives galaxies one. That question belongs to history rather than basic structure. It depends on how early black hole seeds form, how often they merge, how efficiently they grow, and how easily they are lost. It depends on the mass of the galaxy, the density of its centre, the violence of its surroundings, and the long sequence of encounters it experiences. Some galaxies may grow around black holes, some may acquire them later, Some may never create one large enough to recognize. Some may carry one that has gone quiet for nearly the age of the universe. From the outside, these possibilities can look almost identical. A calm galactic center reveals only that nothing obvious is feeding there. It does not immediately reveal whether a dark mass is absent or merely asleep. In the end, gravity beyond the core gives the answer its first shape. A galaxy does not need a black hole in order to be a galaxy. It needs enough mass to remain bound, enough history to assemble stars, and usually a dark matter halo to provide the broad well in which that assembly takes place. The black hole may deepen the center, stir the gas, heat the surroundings, and leave marks across billions of years. It may become one of the most important agents in the galaxy's evolution. But the galaxy itself is larger, older in its structure, and more widely supported than the point of darkness at its center. If a galaxy exists without a black hole, it is not an impossible object. It is a system whose gravity is written across the whole, not concentrated into a single final shadow. Among the great galaxies, the central black hole has become almost part of the expected scenery. A spiral with a swelling bulge, an old elliptical crowded with ancient stars, a massive system at the center of a cluster, all seem to invite the same hidden presence, a compact dark object with the mass of millions or billions of suns. It is not visible in the ordinary sense. It has no surface that shines, no solid edge that reflects light, and no color of its own. Yet when matter falls toward it, the black hole can become one of the brightest engines in the universe. Gas spirals inward, heats under friction and gravity, and forms a blazing disk. Magnetic fields twist. Jets can rise from the central region and pierce outward across distances larger than the host galaxy itself. From far away, an active galactic nucleus may look like a brilliant point. But that point is the sign of a much larger process, a giant black hole feeding at the center of a galaxy. This familiar pattern makes the black hole feel almost necessary. It appears in the Milky Way, it appears in Andromeda, it appears in massive ellipticals where stellar motions reveal enormous hidden masses. It appears in quasars, whose light begins its journey when the universe is young. Over time, the repeated discovery of central giants creates an expectation, and expectation can quietly become assumption. If so many galaxies contain supermassive black holes, perhaps every real galaxy must contain one. But science has to separate frequency from requirement. A common object is not always a required object. A galaxy may often grow a central black hole without needing one in order to exist. This distinction is small in language and large in meaning. The largest black holes are closely linked to the histories of their galaxies, but the link may be a record of shared growth rather than a law of construction. In many large galaxies, the mass of the central black hole tends to rise with the mass and motion of the central bulge. The relationship is not perfect, but it is suggestive. The stars in the bulge and the black hole at the center seem to know something about each other. This does not mean the black hole controls every star, or that it built the bulge by itself. More likely, both are shaped by the same long flows of matter. When galaxies merge, gas can lose angular momentum and fall toward the center. Stars can be scattered into a rounder, denser bulge. Black holes from the merging galaxies may sink inward and combine. The same violent history that builds the central stellar population can also feed and enlarge the black hole. In this way, a correlation emerges, not because the galaxy is hung from the black hole like a lantern from a hook, but because both are products of a shared past. The black hole becomes a fossil of assembly, a dense memory of how much material reached the middle. Once the giant is present, its influence can become profound. A feeding black hole can release energy with extraordinary efficiency, turning the gravitational fall of gas into radiation, winds, and jets. This feedback can heat gas that might otherwise cool into new stars. It can carve bubbles in the hot atmospheres around galaxy clusters. It can slow the growth of a massive galaxy by making its fuel harder to condense. In the largest systems, this may help explain why some galaxies become red, quiet, and old, with little fresh star formation despite being surrounded by reservoirs of gas. The black hole, in this role, is not the seed from which the galaxy sprouts. It is more like a furnace in the centre, sometimes dim, sometimes eruptive, able to change the temperature and motion of gas across astonishing scales. It helps regulate the later life of its host, especially once the host has grown massive enough to trap hot gas and repeated inflows. But a regulator arrives within an existing system. A galaxy can form stars before a giant black hole becomes important, and some galaxies may never reach the conditions that let such a giant dominate their evolution. This is why the word supermassive can mislead. The black hole may be supermassive compared with a star, and still modest compared with its host galaxy. A black hole with millions or billions of solar masses is immense by any human or stellar measure, yet it can remain a small fraction of the total galactic mass. Its power comes from compactness, not from being the main mass of the galaxy. It bends space-time severely near its event horizon. It controls close orbits in the nuclear region. It can produce intense radiation when fed. But across the broad disk and halo, the black hole is no longer the dominant source of gravity. A galaxy without one would be missing an extreme centre, not the mass reservoir that binds its outskirts. The common giant therefore asks for a careful interpretation. When astronomers find supermassive black holes in large galaxies, they are finding evidence of a recurring pathway in cosmic evolution. Massive galaxies tend to have deep central potentials. Their gas can be driven inward by bars, interactions, and mergers. Their dense star clusters may create or deliver black hole seeds. Their long lives provide many opportunities for growth. Once a black hole forms there, every later episode of gas inflow can feed it. Every merger with another galaxy can bring another black hole toward the middle. Over billions of years, growth compounds. The central object becomes difficult to avoid, not because galaxies require it by definition, but because the conditions in large galaxies repeatedly favour its formation and survival. In a giant elliptical galaxy, the presence of a central black hole may be almost expected for this reason. Its absence would be more surprising than its presence. Yet surprising is not impossible. A galaxy might lose its black hole during a merger if gravitational waves carry momentum unevenly from the final coalescence, causing the newly merged black hole to recoil. A smaller galaxy might never form a substantial central seed. A diffuse galaxy might remain too spread out to drive much matter inward. A system stripped by a larger neighbour might keep its stars while losing gas and central structure. These cases do not overturn the general pattern. They occupy the edges, where the rule thins and becomes a question. It is also possible that the central black hole is present but nearly invisible. The Milky Way's central black hole is quiet compared with an active quasar. Yet its existence is clear because nearby stars move around it in precise, tight orbits. At greater distances, this kind of measurement becomes much harder. A dormant black hole in another galaxy may not glow. It may have little gas to feed on, its sphere of influence. The region where its gravity clearly outweighs the surrounding stars may be too small for telescopes to resolve. In that case, a large galaxy may appear black hole-free only because its giant is asleep behind the limits of observation. This is why the commonness of central black holes can be easier to establish than their universality. Many have been found. Many more are strongly suspected. But proving that every galaxy has one is another matter entirely. The common giant becomes a powerful clue, not a final answer. It says that black holes and galaxies often grow together. It says that the brightest beacons in the young universe are not stars alone, but black holes feeding inside young galaxies. At the same time, it leaves room for galaxies whose centres follow another path. A galaxy without a black hole would stand outside the usual rhythm, but not outside gravity. It would be unusual in the way a missing fossil layer is unusual, meaningful because it interrupts an expected story. The presence of supermassive black holes in so many galaxies makes the possibility of absence more interesting, not less. It turns a simple yes or no into a history problem. The question is no longer whether a galaxy can exist without a central black hole. It is whether cosmic history almost always supplies one, and whether any galaxy has managed to remain free of that compact inheritance. In the bright centres of active galaxies, the answer seems obvious. The giant is there, feeding and shaping its surroundings. In quieter galaxies, the answer fades into subtler evidence. Some centres hide a dormant mass. Some may hold only stars. Some may have lost what they once carried. The common giant remains common, but the mystery survives because common things are not the same as necessary things. A black hole may be one of the universe's preferred ways to mark the centre of a large galaxy, while still not being the reason the galaxy can exist. Small galaxies carry some of the oldest clues in the universe because they are not heavy enough to erase every trace of their beginnings. A giant galaxy is a deep archive that has been rewritten many times by mergers, inflows, starbursts, and the slow settling of billions of stars. A dwarf galaxy is different. It can be fragile, irregular, and faint, with a shallow grip on its gas and a history that may have paused early. Some contain only a modest swarm of stars. Some are stretched by the pull of a larger neighbours. Some drift in isolation, barely glowing against the dark. In these small systems, the question of a central black hole becomes more delicate, and in some ways more revealing. If supermassive black holes are common in the great galaxies, dwarf galaxies ask whether the pattern begins everywhere, or only after a galaxy becomes large enough to feed and protect a central seed. They are the quiet edge of the rule, the place where a black hole may be present, absent, wandering, starved, or too faint to betray itself. A dwarf galaxy does not need a black hole to hold itself together. Its stars move inside the gravity of its dark matter halo, its gas, and its own stellar mass. In many dwarfs, the dark matter component may dominate even more strongly than in large bright spirals. The visible galaxy can be only a small lantern inside a much larger invisible well. This means that a central black hole, if present, may be a tiny addition to the overall gravitational structure. It may matter greatly near the nucleus, but the dwarf as a whole can remain bound without it. This makes dwarf galaxies natural candidates for black hole-free systems. They are small enough that the formation of a central black hole is not guaranteed by sheer abundance of material, and their histories can be violent enough to interrupt whatever seed might have formed. The first challenge is that dwarf galaxies are hard to read. Their centres may not be sharply defined. Some do not have a bright bulge at all. Their stars can be scattered unevenly, their gas shaped by bursts of star formation, and their central regions disturbed by stellar winds and supernova explosions. A massive black hole in such a galaxy, if it exists, may be intermediate in mass rather than truly supermassive, perhaps lying between the remnants of collapsed stars and the giants found in large galactic nuclei. Such a black hole may feed only rarely. It may sit in a gas-poor centre and produce no obvious radiation. Its gravitational influence may be smaller than the smallest region current telescopes can separate. The result is a long silence, and silence can be interpreted in more than one way. It may mean absence, It may mean stillness. It may mean that the instrument is not yet sensitive enough. Astronomers search dwarf galaxies for black holes because they may preserve the missing link between ordinary stellar remnants and the enormous black holes seen in quasars. If a dwarf contains a central black hole, that black hole may resemble a seed left over from early cosmic time. It may not have grown much, either because the galaxy never provided enough gas or because feedback from stars kept the centre stirred and thin. These underfed black holes can help reveal how the first seeds formed. If many dwarfs contain them, then black hole seeds may have been common in the early universe. If only a few do, then the birth of black holes may have required special conditions. If some dwarfs contain none at all, then the answer to the larger question becomes clearer. Galaxies can exist without black holes, at least at the low mass end, and black holes are not a universal ingredient of galactic identity. Evidence already points toward variety rather than simplicity. Some dwarf galaxies show signs of active central black holes, including unusual radiation from compact regions, gas moving as though influenced by a dense central mass, or variable light that suggests matter falling into a hidden object. Others show no such signs. The difficulty is that dwarf galaxies can imitate black hole activity through other energetic processes. Young massive stars, supernova remnants, and dense star clusters can also produce bright emission. Gas can move chaotically for reasons unrelated to a black hole. A small active nucleus can be hidden by star formation or confused with it. The faintest signals therefore require caution. The goal is not only to find light, but to prove that the light comes from accretion onto a compact object. In a dwarf galaxy, that proof can be hard to obtain. The uncertainty grows because the central black hole, if it formed, may not stay at the centre. A dwarf galaxy has a shallow gravitational well, and its centre can shift as gas clouds move and star formation bursts reshape the mass distribution. Repeated explosions from massive stars can push gas outward, causing the gravitational centre to breathe and wander. A small black hole may be tugged from the nucleus by interactions with dense star clusters, or by the aftermath of a merger. If two black holes merge inside a small galaxy, the final black hole can receive a recoil from gravitational waves and may be kicked away from the centre, or even out of the galaxy entirely. In a large galaxy, the deep gravitational well may eventually drag such an object back. In a dwarf, escape is easier. The galaxy left behind may still be a galaxy, but its original dark centre may be gone. This possibility gives small galaxies a strange importance. They are not merely weaker versions of large galaxies. They are different laboratories, where processes that are minor in giant systems can become decisive. A burst of star formation that barely disturbs a massive galaxy may reshape a dwarf. A passing encounter that slightly warps a spiral may strip a dwarf of gas. A black hole that would sink toward the centre of a giant may wander for a long time in a smaller system. The boundary between having a nucleus and not having one becomes fluid. Some dwarfs hold nuclear star clusters, compact collections of stars at their centres. These clusters can exist with black holes, without black holes, or perhaps as environments where black hole seeds may form later. A central cluster may therefore replace the role often imagined for a black hole, providing a dense, visible heart without an event horizon inside it. The most careful statement is that dwarf and low-mass galaxies make black hole absence plausible, but not always provable. They loosen the expectation created by giant galaxies. They show that the relation between galaxies and central black holes is not a simple command written into gravity. Instead, it is a probability shaped by mass, environment, gas supply, density, and time. A large galaxy with a central bulge has many chances to grow a black hole, A tiny diffuse dwarf may have few. A compact dwarf with an active nucleus may preserve an ancient seed. Another similar dwarf may show nothing at all. Each case becomes a small clue in a larger census, and the census remains incomplete. This is why the smallest galaxies matter so much to the largest questions. They sit close to the threshold where the usual cosmic pattern may begin. If black holes appear even in many tiny galaxies, then the universe may have seeded them early and widely. If they vanish from the smallest systems, then black holes may be common only above a certain scale. If some dwarfs have lost theirs, then the story includes not only birth but escape. The galaxy without a black hole is most believable here, in the faint outskirts of the galactic population, where gravity is real but modest, where histories are easily disturbed, and where darkness may not have had enough time or fuel to grow into a central giant. Small galaxies therefore do not settle the mystery, but they narrow its shape. They reveal that the black hole is not the first requirement of a galaxy. It is an outcome that may or may not follow, depending on conditions. In their dim centers, the universe may be showing that some galaxies carry a hidden black hole, some carry only stars, and some remain undecided to every instrument so far built. The clue is small, but it is not weak. It suggests that the missing center may be most likely in the faintest places, where the galaxy survives not because a black hole anchors it, but because its dark halo, stars, and long quiet history are enough. Finding a black hole means searching for something that does not give back light. The object itself is defined by absence, by the border beyond which signals cannot return, and so astronomy has to study the world around it instead. A central black hole is revealed not by a visible surface, but by the behavior of stars, gas, radiation, and space-time near a galaxy's core. This makes the search both powerful and uncertain. When the evidence is strong, it can point to an unseen mass packed into a region too small and too heavy to be explained by ordinary stars. When the evidence is weak, the same silence can mean several things at once. A galaxy may hold no black hole. It may hold a black hole too small to measure. It may hold one that is not feeding. It may hide its center behind dust or distance. The methods used to find black holes are therefore also methods for understanding why absence is so difficult to prove. The cleanest path is motion. Gravity writes itself into orbits. And stars close to a central black hole move faster than they would if only visible matter were present. In the Milky Way, stars near the galactic center can be followed as they sweep around a dark, compact mass. Their paths show not a vague heaviness, but a concentrated object occupying a tiny volume compared with the surrounding star field. The stars do not need the black hole to hold the entire Milky Way together, but near the center, they respond to it with unmistakable speed. In more distant galaxies, the same principle remains, though the evidence becomes harder to separate. Individual stars may blur together into a single glow, so astronomers measure the broadening of spectral lines, the subtle spreading of colors caused by many stars moving at different speeds. A central black hole can make these motions faster in the nucleus, but dense star clusters, unusual stellar populations, and the shape of the galaxy can complicate the reading. Motion remains one of the strongest clues, but only when the telescope can resolve the region where the black hole's gravity clearly dominates. This region is called the sphere of influence, a useful phrase for a simple idea. It marks the inner zone where the black hole contributes more to local stellar motion than the surrounding stars do. If that zone appears large enough in the sky, the black hole can be weighed. If it is too small, the black hole may vanish into the combined light and gravity of the galactic center. Distance, therefore, becomes a kind of fog. A massive black hole in a nearby galaxy may be measurable, while a smaller black hole in a farther dwarf galaxy can remain beyond reach. Non-detection may reflect absence, but it may also reflect scale. The same instrument that exposes a giant in one galaxy may miss a quiet seed in another. Gas offers another method. In some galactic centers, gas forms a rotating disk around the nucleus. If the gas moves in orderly circles, its speed can reveal the enclosed mass. Faster motion near the center suggests a compact gravitational source. This technique can be precise when the gas is calm, but gas is rarely a perfect witness. It can be pushed by stellar winds, shocked by supernovae, stirred by magnetic fields, or driven into turbulence by bars and mergers. A black hole may make gas whirl, but young stars can also make gas glow and move. In small galaxies especially, where star formation can dominate the central light, the line between black hole activity and ordinary stellar violence can become blurred. Gas can testify, but it can also be confused. Radiation gives the most spectacular evidence when a black hole is feeding. Matter falling inward forms an accretion flow, heating as gravitational energy becomes light. The center can shine across radio waves, visible light, ultraviolet light, and high-energy emission. In powerful active galactic nuclei, the black hole announces itself from across the observable universe. In weaker systems, the signal may be a compact radio source, a flickering nucleus, or spectral fingerprints from gas excited by energetic radiation. Such signs can reveal black holes too distant or too small for direct orbital measurements. Yet radiation depends on food. A starving black hole may be nearly dark. A black hole surrounded by little gas can sit for immense stretches of time without producing a clear beacon. Bright activity proves feeding. It does not prove that all quiet centers are empty. Some black holes reveal themselves through changing light. If gas falls inward unevenly, the central source may brighten and fade. If a star passes too close, it may be torn apart by tidal forces, producing a flare as debris heats around the black hole. Such events can expose a dormant black hole that was invisible before the star arrived. But these flares are rare, brief by cosmic standards, and not every galaxy offers one during observation. A galaxy without a recorded flare may have no central black hole, or it may simply not have sacrificed a star at the right moment. Time becomes another limit. Astronomy watches long-lived systems through narrow windows, and many black holes may spend all of that window in silence. Radio observations add a different kind of clue. Jets and compact radio cores can betray accretion and magnetic activity near a black hole. Some jets stretch far beyond the host galaxy, inflated by energy released close to the event horizon. Others are faint and local. In massive galaxies, radio feedback can mark a central black hole even when optical light is obscured. In smaller galaxies, radio sources can overlap with signals from supernova remnants and stellar nurseries. The evidence must be assembled, one layer at a time. No single clue always works. Each method has a strength and a blind spot. Stellar motion is direct, but demands resolution. Gas motion can weigh a central mass, but only if the gas behaves cleanly. Radiation can reveal active feeding, but only when matter is falling in. Flares can expose dormant black holes, but only when rare events occur. Radio jets can be dramatic, but their absence means little. This creates an uneven map of certainty. The best studied nearby galaxies may offer strong measurements. Distant or faint galaxies may offer only limits. A black hole can be ruled out above a certain mass, while a smaller one remains possible. The phrase "no black hole" is therefore often replaced by a more careful statement: no black hole has been detected, or no black hole larger than a certain mass is allowed by the data. The difference is the shape of honest evidence. There is also the problem of what counts as central. A black hole may not sit exactly at the centre of its galaxy. It may wander after a merger, recoil from a gravitational wave kick, or drift inside a shifting dwarf galaxy whose mass distribution changes. Searching only the nucleus could miss such an object. A galaxy might appear to lack a central black hole while carrying a displaced one in its outskirts, or in a dense star cluster away from the brightest centre. A galaxy could be without a central black hole and still contain black holes elsewhere, both ordinary remnants from dead stars and perhaps a heavier wanderer left by a disturbed past. The question is not whether black holes exist somewhere in the galaxy, but whether one occupies the central role that large galaxies often display. Modern astronomy is steadily improving this search. Sharper infrared observations can peer through dust near galactic centres. Radio interferometers can combine distant antennas to resolve fine details. Space telescopes can detect faint high-energy sources. Surveys can monitor many galaxies for flares and changing nuclei. Gravitational wave observatories may eventually reveal mergers involving intermediate mass black holes, giving indirect clues about where such objects live. Each improvement narrows the silence. It may turn empty centres into detections. It may also strengthen the case that some galaxies truly have no central black hole above any meaningful mass. Both outcomes matter. Detection explains how common black holes are. Continued absence, under better limits, shows where the pattern breaks. In the search for a galaxy without a black hole, the methods become part of the mystery. The universe does not label its empty centres. It offers motions that are too fast, gas that glows strangely, light that flickers, jets that rise, stars that vanish into flares, and sometimes nothing at all. From these signs, astronomers build a case. The strongest cases reveal compact darkness. The quietest cases remain open. A black hole may be hidden in the stillness, or the stillness may be real, until the centre is weighed and watched from more than one angle. The missing black hole remains less a conclusion than a boundary between what has been seen and what may still be there. A galaxy without a central black hole is not a hole torn in the laws of astronomy. It is a possible path through cosmic history, a system whose stars gather, orbit, and age without placing an event horizon at the middle. The difficulty is that this possibility does not announce itself with drama. There is no obvious sign that says the centre is empty. There may only be a calm nucleus, a faint star cluster, a disk of gas with no glow, and motions that do not demand a hidden mass. Such a galaxy would look ordinary. Its stars would trace the gravity of the whole system. Its gas could cool into clouds. Its older populations could drift in long orbits. The absence would matter not because the galaxy would fall apart without the black hole, but because it would reveal that one familiar companion of galactic growth is not universal. To understand how such a galaxy could exist, the story has to begin before the black hole, when galaxies are only forming. The early universe contains differences in density, and the slightly denser regions gather more matter as the universe expands. Dark matter forms the first broad wells. Gas falls into those wells and begins to heat, cool, and collect. Stars appear where the gas becomes dense enough to collapse. A young galaxy can therefore begin as a star-forming system inside a dark halo, without needing a central black hole to start the process. A black hole seed may form later, or it may form early in only some places. Several routes are possible. A massive first star may die and leave a black hole remnant. A large gas cloud may collapse directly into a heavier seed under special conditions. A crowded star cluster may drive repeated mergers that build a central object. Each route depends on local details: gas temperature, chemical enrichment, rotation, turbulence, radiation from nearby stars, and the depth of the dark matter halo can all change the outcome. If none of these paths succeed, The young galaxy may continue forming stars without a central black hole. In a small halo, this may be especially plausible. Early stars can stir or eject the remaining gas. Supernova explosions can heat the center and reduce the supply available for collapse. Radiation can prevent gas from cooling efficiently. Instead of feeding a growing seed, the galaxy may spend its early life losing the material that might have built one. In this version of the story, the missing black hole is not removed. It simply never forms. The galaxy grows as a modest stellar system, shaped by dark matter and star formation, while its center remains ordinary matter rather than a compact abyss. Another path involves starvation. A small seed black hole may be born, but never grow into a central giant. It may remain so light that its influence is almost invisible, closer to the mass of stellar remnants than to the supermassive black holes in giant galaxies. In strict terms, this would not be a black hole-free galaxy, but it shows why the boundary is hard to draw. A galaxy can function almost as though no central black hole exists if the object is too small, unfed, and dynamically unimportant. The most interesting case, however, is the stronger one: no central black hole at all. For that to happen, either no seed forms or a seed is lost. Loss is possible because galaxies do not grow gently. They merge, brush past one another, strip gas, exchange stars, and shake their own centers. In a galaxy merger, two central black holes may sink inward through the surrounding stars and gas. If they merge, the gravitational waves emitted in the final moments can carry momentum unevenly. The resulting black hole can receive a kick. In a massive galaxy, this recoil may only displace it, sending it wandering before gravity and friction slowly pull it back. In a dwarf galaxy, the same kick may exceed the escape speed. The black hole leaves, and the galaxy remains. Such a system would once have had a dark center, then lost it to the physics of black hole growth. This creates a strange inversion. A merger can help build supermassive black holes in large galaxies, but in small galaxies it may remove them. The outcome depends on mass, velocity, geometry, and timing. A shallow galaxy is easier to empty of its central compact object. It is also easier to disturb. Star clusters may shift the nucleus. Bursts of star formation may change the gravitational center. The black hole may fail to remain fixed where astronomers expect it. It may become a wanderer, neither central nor easy to find. A galaxy that appears to have no nuclear black hole may therefore have lost it completely, or may have displaced it into the dark outskirts. Both possibilities loosen the link between galaxy and central black hole. Stellar feedback offers a quieter route toward absence. In low-mass galaxies, massive stars can act as engines of disruption. Their winds and explosions push gas outward, and because the galaxy's gravity is weak, the gas may not settle back quickly. Repeated cycles of gas expulsion and return can flatten the central density of dark matter and stars. They can also prevent long-lasting inflow toward the center. Without steady inflow, a black hole seed has fewer chances to form and grow. The central region remains a changing place rather than a stable reservoir. Instead of building a compact nucleus, the galaxy builds scattered generations of stars. The more irregular the history, the less certain the birth of a central black hole becomes. Some galaxies may simply not be massive enough to follow the black hole pattern seen in large systems. A threshold may exist, not a sharp wall but a rising probability. Above a certain scale, gas inflow, mergers, and dense stellar centers make black holes common. Below it, they become optional. A diffuse galaxy with low central density may never compress enough material into the right conditions. A galaxy stripped by a larger neighbor may lose gas before a seed can grow. A satellite galaxy may orbit for billions of years as a faint collection of old stars. its center too thin and quiet to produce or feed a central black hole. Such systems would be galaxies with different histories, surviving by the gravity of their halos and stars rather than by any central engine. Proving this is the hard part. The best evidence for a truly black hole-free galaxy would require more than a quiet nucleus. It would need measurements showing that no compact central mass exists above very low limits. Stellar motions would have to be mapped in enough detail to rule out a hidden object. Gas dynamics, if present, would need to show no central excess. Radiation surveys would need to find no active source, while also acknowledging that a non-feeding black hole may produce no light. Even then, there may always be room for an extremely small black hole below detection. The claim would therefore be practical rather than absolute. No central black hole of any astrophysically significant mass appears to exist. In science, that may be enough to reshape the pattern. A galaxy without a central black hole would not need to be completely empty of all black holes. It could still contain stellar mass black holes scattered through its old populations, the remnants of massive dead stars. It could still contain neutron stars, white dwarfs, and other compact remnants. The specific absence is the central one, the massive object that often sits in the nucleus and grows with the host. This distinction matters because black holes are ordinary outcomes of stellar evolution, while central massive black holes are records of galactic history. The image that remains is not of an impossible galaxy, but of a quiet alternative. In such a galaxy, the core may be ruled by a dense star cluster, or by no special structure at all. Its stars may move in response to a smooth central mass distribution rather than to a compact object. Its gas may form stars without producing an active nucleus. Over cosmic time, it may fade, merge into a larger system, or continue as a small satellite. If it later falls into a giant galaxy, its lack of a central black hole may become hard to notice. This is why the possibility is both modest and profound. A black hole-free galaxy does not overturn gravity. It clarifies galaxy formation. It says that black holes are not the roots from which all galaxies grow, but outcomes that arise when certain histories allow them. Some galaxies may inherit them, some may build them, some may lose them, and some may never know them. The center can be dark because a black hole is hidden there, or dark because there is nothing compact enough to reveal. Between those two forms of darkness lies the open gap where the answer waits. The question of a galaxy without a black hole reaches back to a deeper beginning. Before the first nuclei, before the giant ellipticals, and before the universe has settled into the web of galaxies, it reaches the seed problem. Supermassive black holes are not merely heavy versions of ordinary stellar remnants. They can contain millions or billions of solar masses, and some are already seen powering brilliant quasars when the universe is still young. A black hole can grow by swallowing gas and merging with other black holes, but growth takes time, and the earliest giants appear so soon in cosmic history that their first seeds must have formed efficiently, or started unusually large, or fed with remarkable speed. The answer matters for black hole-free galaxies because a seed is the first claim a black hole makes on a future galactic center. If seeds form almost everywhere, then most galaxies may inherit one from birth. If seeds form only in rare conditions, then many galaxies, especially small ones, may begin and perhaps remain without them. The seed problem therefore asks not only how the largest black holes become so large, but whether every galaxy is expected to receive the first dark grain from which a central giant can grow. The most familiar route begins with stars. Massive stars live quickly and die violently. When their cores collapse, they can leave behind black holes with masses of a few suns, or more in special cases. In the early universe, the first stars may have been larger than most stars forming now, because the gas around them contains almost no heavy elements. Heavy elements help gas cool and fragment into smaller clouds. Without them, primordial gas may collapse into fewer, larger stars. If some of those first stars leave black hole remnants, those remnants could become the original seeds. Stars form in young galaxies. Some die as black holes. A few of those black holes sink toward dense centers and begin to feed. Yet the simplicity has a difficulty. A seed left by a star begins relatively small compared with a supermassive black hole. To become a billion solar masses while the universe is still young, it needs rapid, sustained growth. Gas must fall inward again and again without being blown away by radiation, supernovae, or the black hole's own feeding. In some young galaxies this may happen, in others it may not. The stellar remnant path therefore does not automatically give every galaxy a meaningful central black hole. It gives many galaxies a chance, and chance is not inevitability. A second route begins not with the death of a star, but with the collapse of gas itself. In rare early environments, a large cloud of primordial gas may avoid breaking into many stars. Instead, it may flow inward as one great mass, forming a much heavier black hole seed directly. This direct collapse idea is attractive because it starts closer to the needed scale. A heavy seed has less distance to grow before becoming a quasar engine, but the conditions are demanding. The gas must remain hot enough to resist fragmentation, while still losing enough energy to collapse. Molecular hydrogen, which helps primordial gas cool, may need to be suppressed by radiation from nearby young stars. The cloud must funnel material inward faster than ordinary star formation can consume it. These requirements make direct collapse powerful but selective. If this is the main route to massive seeds, then black holes may be born only in special places. Some young galaxies receive a heavy central seed, while many others do not. The possibility of a galaxy without a black hole becomes easier to imagine under such a selective universe. A third route uses dense star clusters. In a crowded young cluster, massive stars and stellar remnants can sink toward the middle through repeated gravitational encounters. Collisions and mergers may build a very massive star, or a chain of black hole mergers may create an intermediate mass black hole. This object could then become the central seed of a galaxy. The cluster route begins with ordinary star formation, but relies on extreme density and timing. The cluster must be compact enough for heavy objects to meet before the most massive stars explode or scatter the system. Again, the conditions are not universal. Some galaxies may form suitable clusters, others may form diffuse associations that never build a central object. The seed problem becomes a map of probabilities. Different environments plant different seeds, and some plant none. Once a seed exists, its survival is another question. A young black hole must stay near the central reservoir if it is to become a galactic nucleus. But early galaxies are messy. Gas moves in clumps. Stars form in bursts. Supernovae push matter outward. Small galaxies merge at odd angles. A seed black hole can be dragged, starved, or displaced. If it forms away from the deepest part of the halo, it may wander for a long time. If the galaxy is shallow, the seed may be kicked out by later black hole mergers. Even if the universe creates many seeds, it may not keep all of them in the centers where astronomers expect to find them. A galaxy can inherit a seed and still become, in practice, a galaxy without a central black hole. Feeding is the next filter. Black holes grow only when matter reaches them. This sounds easy inside a gas-rich young galaxy, but angular momentum is a stubborn barrier. Gas tends to orbit rather than fall straight inward. It must lose some of its sideways motion through friction, turbulence, bars, spiral structures, gravitational torques, or mergers. Large galaxies provide many opportunities for this inward transport. Small, irregular, or gas-poor galaxies may not. A seed can sit in the middle and remain nearly unchanged for billions of years if little material reaches it. Such a galaxy is not black hole free, but it shows how a central black hole can be present without becoming important. If the seed never forms at all, the outward appearance may be similar: a quiet centre, no active nucleus, and stellar motions governed by distributed mass. The earliest quasars sharpen the mystery. Their existence shows that at least some black holes grow extremely fast in the young universe. They are like distant lighthouses, proving that the growth pathway can work under the right conditions. But a lighthouse does not show the fate of every shore. Bright quasars are the visible extremes, the successful cases where a seed forms, feeds, and becomes enormous. They don't reveal how many young galaxies fail to produce seeds, or produce seeds that never grow. The silent majority may be harder to understand than the luminous minority. This unevenness leaves room for genuine absence. A galaxy that forms in a low-mass halo may never make the right kind of first-star cluster. Its gas may be heated or stripped before direct collapse becomes possible. Its earlier stellar remnants may be scattered rather than gathered. Its later mergers may be too small or too disruptive to build a central object. Over time, it can still remain a galaxy. It can still form stars, orbit a larger neighbour, hold dark matter, and preserve an ancient population. What it lacks is not gravity, but a particular episode in its history, the creation and retention of a central seed. The absence is not a wound, it is a skipped step. In larger galaxies, skipped steps become less likely because history offers more chances. Many stellar remnants form, many clusters sink, many mergers occur. Gas has deeper wells to fall into. Even if one seed is lost, another may arrive. This may explain why massive galaxies so often carry central black holes, while smaller galaxies show more variety. The seed problem therefore turns the yes or no question into a question of scale. At the high mass end, central black holes may be nearly guaranteed by repeated opportunity. At the low mass end, they may be conditional. Between the two lies a transition where some galaxies carry seeds, some grow them, some lose them, and some never form them. The first black holes in the universe remain partly hidden behind distance and time, but their consequences survive in galactic centers. Every supermassive black hole is a record of a seed that formed and endured. Every quiet dwarf without evidence for one may be a record of a seed that failed, fled, or never appeared. To ask whether a galaxy can exist without a black hole is therefore to ask how generous the early universe is with its darkest seeds. The answer may not be one rule, it may be a branching story, where the largest galaxies almost always inherit darkness, while smaller systems reveal the gaps in the planting. Somewhere in those gaps, a galaxy may continue through cosmic time with stars at its centre instead of a horizon, carrying the memory of a beginning in which no seed took root. A black hole is often imagined as the final thing a galaxy cannot lose, a dark weight buried in the centre that the system must carry forever. Yet gravity is not only a force of gathering, it can also become a force of exile. In a universe where galaxies merge, clusters scatter, and space-time ripples during violent encounters, even a massive black hole can be displaced from the place where it formed. The idea seems strange because black holes feel permanent, but their permanence is local. They can move, they can be pushed, pulled, dragged, and in some cases thrown away. A galaxy that once had a central black hole may therefore become a galaxy without one, not because the black hole disappeared, but because the galaxy failed to keep it. This possibility turns the missing centre into a history of escape. The most important pathway begins with a merger. Galaxies do not live in isolation forever. They fall together along the cosmic web, pass through one another, strip each other's gas, and sometimes combine into a larger system. If both galaxies carry central black holes, those black holes are brought into the new shared halo. At first, they remain far apart, each surrounded by its own stars. Over time, gravitational interactions with surrounding matter draw them toward the center. This slow inward sinking is called dynamical friction, a process in which a massive object moving through stars and gas leaves a wake behind it. The wake pulls backward, stealing orbital energy and causing the object to spiral inward. For black holes, this means that a galactic merger can gradually become a black hole pairing. The two dark masses approach until their motion is controlled mainly by each other. When the pair becomes close enough, it forms a binary black hole. The black holes orbit their common center, scattering nearby stars and stirring the nucleus. Every star that passes close can carry away a little orbital energy, tightening the pair. Gas can also help. If it forms a disk around them and drains angular momentum from the system, eventually the binary loses energy through gravitational waves, ripples in space-time that carry energy and momentum outward. The black holes draw together faster. A new black hole forms from the union, more massive than either parent, but not always at rest. If the gravitational waves are emitted symmetrically, the final black hole remains near the center. If they are emitted unevenly, the waves carry momentum one way, and the black hole recoils the other way. This gravitational wave kick can be gentle, or it can be strong enough to matter for an entire galaxy. The strength of the kick depends on the masses and spins of the merging black holes. If the two black holes have very different masses, or if their spins are tilted in certain ways, the radiation can become lopsided. Momentum must be conserved, so the final black hole receives a push. In a giant galaxy with a deep gravitational well, the push may send the black hole on a long wandering orbit through the central regions. It may pass through the nucleus again and again, slowed by dynamical friction, until it finally settles back. For millions or billions of years, the galaxy may have an off-center black hole, a dark traveller carrying its own cluster of stars or a small disk of gas. In a smaller galaxy, the same kick can be more decisive. A dwarf galaxy has a lower escape speed, its grip is shallower. A recoil that merely displaces a black hole in a giant system may eject it completely from a dwarf. The galaxy remains, but its central black hole is gone. This is one of the clearest natural routes to a black hole-free center. The absence is not primordial. It is the aftermath of a merger that succeeded too violently. The black hole grows by joining another, and that very act launches it away. The remaining galaxy may settle into a quiet state, with stars still bound to the dark matter halo, but no compact object at its nucleus. If gas remains, it may form stars around a center now ruled by ordinary matter. If the galaxy has lost much of its gas, it may fade as an old stellar system. Ejection can also happen before black holes merge. When several massive black holes are brought together through repeated galaxy mergers, their gravitational dance can become unstable. A binary may interact with an intruder, and one black hole can be flung outward, while the remaining pair becomes more tightly bound. In a massive galaxy, the expelled black hole may remain bound on a wide orbit. In a smaller system, it may leave entirely. If the black hole being expelled is the only central black hole the galaxy has, the result is again a missing nucleus. The galaxy survives the interaction, but the compact object that might have regulated its center becomes a wanderer in intergalactic space, or a faint object moving through the halo of a larger neighbor. These wandering black holes would be difficult to find. A black hole alone in space is nearly invisible unless it passes near gas or stars. If it carries a small cluster of bound stars with it, that cluster may appear as a compact object moving unusually fast. If it drags a disk of gas after a recoil, it may shine for a time as an off-center active source. Otherwise, it drifts quietly, not gone from the universe, but gone from the role it once played. The host galaxy, meanwhile, may present a calm center. Observers might search the nucleus and find no strong evidence of a black hole, without knowing whether the missing object was never born or was thrown away long ago. Recoil, therefore, complicates the meaning of absence. A black hole-free galaxy may be born empty, or it may be made empty by escape. The surrounding galaxy may still carry scars of the event, though they can be subtle. A recent merger can disturb stellar shells, tidal streams of warped disks, or irregular gas. A displaced black hole may leave a gap in the central star cluster, or a slight asymmetry in the motions of stars. An active source located away from the galactic center may hint at a recoiling black hole. But these signs fade. Stars mix, gas cools or is expelled. The galaxy relaxes. After enough time, the missing black hole becomes a historical fact with little visible trace. This is why the census of black holes is also an attempt to reconstruct events that may have happened billions of years ago. The same physics affects black holes that remain. A recoil that does not escape can still delay feeding by moving the black hole away from the densest gas. A wandering black hole may spend long periods starved, slowing its growth in a small galaxy. Repeated disturbances can prevent a black hole from settling at all. Instead of one stable dark center, the system may host a restless compact object whose location changes with time. From the standpoint of galaxy evolution, centrality is not guaranteed. A black hole must not only form, it must also stay where fuel and stars can gather around it. This gives the absence of a central black hole a dynamic meaning. It may not point to a failure of black hole formation, but to the success of later gravitational violence. Ejection also reveals how different large and small galaxies can be. In a massive elliptical, escape is difficult. The black hole may recoil, but the galaxy's deep potential keeps it bound, and over time it returns. In a dwarf galaxy, the boundary is more fragile. The same merger physics can transform the nucleus permanently. Small galaxies are easier to empty, disturb, and reshape. If black hole-free galaxies exist, many may owe their condition to this imbalance between the strength of the kick and the depth of the host. The universe does not need to prevent black holes from forming in order to create such systems. It only needs to let some of them leave. A galaxy whose black hole has escaped is a quiet paradox. The most compact object in the system is no longer at the center, and the galaxy continues without it. Its stars remain bound by distributed gravity. Its dark matter halo keeps its broad shape. The black hole becomes a lost remnant of the galaxy's past, moving somewhere beyond the place where it once marked the nucleus. In that image, the center is not empty because nothing happened there. It is empty because too much happened. A merger, a recoil, a gravitational slingshot, or a long wandering escape has turned the old heart into a traveller. The galaxy that remains is not impossible. It is a survivor of motion, carrying a missing center as evidence that the darkest objects can be displaced by the deeper choreography of gravity. A quiet galactic center can feel like an answer, but in astronomy, quiet is often only the beginning of the question. A black hole does not shine by its own surface. It reveals itself when surrounding matter gives it away, when stars move too quickly, gas heats too fiercely, or a compact source flickers from the center. Without such witnesses, even an enormous object can seem absent. This is why the search for a galaxy without a black hole must pass through a careful distinction. There is the galaxy whose centre truly contains no massive black hole, and there is the galaxy whose black hole is dormant, starved, hidden, or too small for present instruments to expose. From far away, these two galaxies can look almost the same. Both may have a calm nucleus, both may lack a bright active core, both may show no obvious jets, no violent accretion disk, and no sudden flare during the years they are watched. The difference lies not in the first appearance of silence, but in what that silence allows after the deepest possible measurements are made. A dormant black hole is not a weak black hole in the fundamental sense. It may have millions of solar masses and still remain faint if very little gas reaches it. Feeding is the difference between a dark mass and a blazing nucleus. Around an active black hole, gas spirals inward, heating as it loses energy and angular momentum. The falling material emits radiation, and the central region can outshine the surrounding stars. Around a dormant one, the fuel supply may be thin, hot, or unable to settle into a disk. The black hole waits without a bright announcement. It may swallow a little matter from time to time, but not enough to produce a clear signal. In a gas-poor galaxy, or in a nucleus where stellar winds are weak and diffuse, the black hole can become almost invisible. Its gravity remains, but its light is missing. The Milky Way offers a useful contrast. Its central black hole is not a quasar. It does not flood the galaxy with brilliant radiation, yet it is not unknown, because nearby stars trace tight orbits around an invisible compact mass. Their motion exposes what the black hole itself withholds. In a more distant galaxy, the same kind of proof may be impossible. Individual stars blur together. The central region may be too small on the sky. The sphere of influence may fall below the instrument's resolving power. Then a dormant black hole could hide in plain sight. Not because it is mysterious in a magical way, but because its measurable effects are confined to a region too tiny and too faint to separate. Non-detection becomes a statement about limits. It says that no black hole has been found above a certain mass, with a certain method, under certain assumptions. It does not always say that no black hole exists. Dust adds another kind of concealment. Galactic centers can be crowded with gas and obscuring material. Visible light may be blocked or scattered before it reaches telescopes. Infrared observations can pass through some of this dust, and radio waves can often reveal deeper structures. But every wavelength has its own blind spots. A center that looks quiet in one kind of light may show activity in another, or the opposite may happen. A source that appears energetic may turn out to be powered by young stars rather than by a black hole. The center of a galaxy is rarely a clean laboratory. It is a crowded neighborhood of old stars, stellar remnants, hot gas, magnetic fields, dust lanes, star clusters, and sometimes recent explosions. To identify a black hole there, astronomers must subtract many other possibilities. To identify absence, they must subtract even more. A small black hole deepens the problem. In a dwarf galaxy, the central black hole, if present, may have only thousands or tens of thousands of solar masses. Such a mass is enormous compared with a star, but modest compared with a galactic nucleus. Its gravitational reach may be small, its feeding may be rare, it may produce radiation that can be confused with bright stellar remnants or compact star-forming regions. If the question is whether every galaxy has a supermassive black hole, then a small seed might not count in the same way. If the question is whether any black hole exists at the center, then even a small hidden remnant matters. The meaning of absence depends on the scale being tested. A galaxy may lack a central giant while still hosting a lesser black hole. It may lack an active nucleus while still hosting a dormant one. It may lack a centered black hole while carrying a wandering one somewhere in its halo. Each version answers a different question. Dormancy also changes with time. A black hole that is silent now may have been active in the past. Galaxies preserve traces of older activity in heated gas, faint radio bubbles, disturbed dust, or chemical patterns shaped by earlier outflows. These traces fade, and not every old episode is recoverable. A galaxy could look inactive today while its central black hole once helped regulate its gas. Another galaxy could have a black hole that has never fed significantly, leaving almost no historical mark. A single observation catches only one moment in a long life. Galactic time is slow, and black hole feeding can be episodic. Long quiet intervals may separate short bursts of activity. To say that a centre is quiet is therefore not to say that it has always been quiet, or that it will remain so. A dormant black hole is a potential engine with no current flame. The problem is sharpened by the way black holes grow. Growth depends on supply. A black hole surrounded by a rich reservoir of cold gas may become active, while the same black hole in a depleted galaxy may starve. A merger can drive gas inward and wake the nucleus. A bar in a spiral galaxy can slowly guide material toward the centre. A passing cloud can briefly feed the black hole. Without such events, the black hole may remain nearly unchanged for immense periods. This means that the observed population of active black holes is only a fraction of the existing population. The luminous ones are the ones caught eating. The silent ones may be far more numerous. Any search for black hole-free galaxies must therefore avoid confusing hunger with non-existence. The empty table does not prove there is no guest in the room. There is a more subtle possibility as well. A galaxy may have a dense nuclear star cluster that imitates some roles of a black hole while hiding the absence of one. Such clusters can dominate the central light and shape the motions of nearby stars. They may form through repeated star formation, or by the sinking and merging of smaller clusters. In some galaxies, a nuclear star cluster and a black hole may coexist. In others, the cluster may be present alone. If a cluster explains the central motions without requiring a compact dark mass, then the case for absence strengthens. But the cluster itself must be modelled carefully. Its mass, shape, and stellar population affect the calculation. A black hole could still sit inside it, small enough not to disturb the measurement strongly. The cluster becomes both an alternative and a hiding place. To move from silence to true absence, evidence must converge. Stellar motions must place strict upper limits on any compact central mass. Gas dynamics must fail to require a black hole. Multi-wavelength surveys must find no sign of accretion. The galaxy's centre must be resolved well enough that a significant object could not easily hide. Even then, the conclusion remains cautious, because nature can always place an object just below the threshold. This caution is not weakness. It is the discipline of studying darkness. The strongest claim may be that a galaxy contains no central black hole massive enough to affect its nucleus in the expected way. For understanding galaxy formation, that may still be profound. Quiet does not mean empty, but it can become evidence when the quiet is measured deeply enough. Each improved telescope lowers the mass that can hide. Each longer survey reduces the chance that brief activity was missed. Each sharper map of stellar motion narrows the room for a central object. Some quiet centres will eventually reveal black holes. Others may remain quiet even as the limits tighten, becoming stronger candidates for genuine absence. The mystery is not solved by silence alone. It is solved, if it can be solved, by silence surrounded by constraints. In that careful space, a galaxy without a central black hole remains possible, but never casual. It is not found simply by looking for darkness. It is found by proving that the darkness has no weight at the centre. Not every galaxy grows around a bright bulge, a crowded nucleus, and a central giant waiting to feed. Some galaxies spread their stars in thin disks with almost no central swelling. Some are so faint and diffuse that their light seems barely attached to the dark matter halo that holds them. Some are irregular, broken, stripped, or stretched by the gravity of larger neighbours. These systems matter because they loosen the old picture of galactic development. A galaxy is not a single kind of object wearing different shapes. It is a family of histories, and different histories can lead to different centres. In one path, gas falls inward, stars crowd into a bulge, mergers stir the nucleus, and a black hole seed grows with repeated meals. In another path, the galaxy remains light, extended, and calm, never building the dense central environment that makes a massive black hole likely. The possibility of a galaxy without a black hole becomes more believable once the universe is seen not as a factory producing identical structures, but as a long experiment in many ways of assembling matter. Bulgeless galaxies are especially important because the strongest connections between black holes and their hosts often involve the central bulge. A bulge is a dense, rounded concentration of stars near the middle of a galaxy. It can form through mergers, through the slow rearrangement of disk material, or through early collapse when gas collects rapidly. Bulges are good places for black holes to grow because they mark deep central gravitational wells. Gas can be driven inward. Star clusters can sink. Mergers can deliver existing black holes to the same centre. When a galaxy lacks a bulge, the central conditions may be different. The disk may dominate all the way inward. Stars may follow calmer, flatter orbits. Gas may form stars without being forced into a compact nucleus. A black hole may still exist there, and some bulgeless galaxies do host central black holes, but the expectation weakens. The missing bulge becomes a clue that the galaxy has avoided at least part of the history that often builds a central giant. This does not mean bulgeless galaxies are simple. A disk can grow bars, spiral arms, rings, and star-forming knots. A bar, which is an elongated structure of stars crossing the inner disk, can slowly move gas toward the centre. Over long times, this may build a compact central feature, sometimes called a pseudo-bulge, made not by violent mergers but by internal rearrangement. Such a centre may feed a modest black hole if one exists. Yet this growth can be slow and inefficient compared with the dramatic inflows caused by major mergers. A galaxy that lives quietly, with no large collision and no dense classical bulge, may remain underbuilt at its core. It may have a nucleus of stars, or a small black hole, or neither. Its structure says that central black hole growth is not merely about age, but about the specific routes matter takes inward. Diffuse galaxies carry the question even farther. Some galaxies have large sizes but very low surface brightness, meaning their stars are spread thinly across a wide region. Others, often called ultra-diffuse galaxies, can be as extended as much larger systems while containing far fewer stars. Their centres may be faint, soft, and poorly concentrated. In such systems, the usual pathways to a massive central black hole may be interrupted. A low-density stellar body produces fewer close encounters. Thin gas may fail to collect efficiently. If the galaxy has lost gas early, it may have little fuel for either new stars or black hole growth. Dark matter may dominate the gravitational field, but dark matter does not cool into a shining disk, or fall directly into a central point in the same way ordinary gas can. It holds the galaxy broadly, not compactly. The galaxy can survive as a wide, dim cloud of stars without ever building a strong nucleus. These diffuse systems challenge the habit of thinking that every galaxy is a scaled version of a large spiral or elliptical. Some may be failed giants that lost gas before forming many stars. Some may be puffed up dwarfs stirred by internal feedback or external tides. If a diffuse galaxy formed in a massive halo but made few stars, it might once have had conditions suitable for a black hole seed. If it is truly a low-mass system spread across a large volume, a central black hole may be less likely. The same appearance can hide different histories. A faint, broad galaxy might be a system that never had the density to form a central black hole, or a system that once had one but lost the gas needed to reveal it. The shape alone does not decide the answer, but it widens the range of possible answers. Irregular galaxies also show that order is not required for survival. They may lack grand spiral arms, smooth bulges, or clean central symmetry. Their stars form in uneven patches. Gas clouds can dominate their visible structure. Supernovae can carve cavities, push material outward, and make the galaxy breathe over time. In a small, irregular galaxy, the center itself may be hard to define. The brightest region may not be the center of mass. A star-forming complex may glow more strongly than the older stellar population. If a black hole exists, it may not sit neatly at the brightest point. If none exists, the galaxy can still continue forming stars wherever gas becomes dense enough. Such galaxies emphasize that a central black hole belongs to one kind of galactic organization, not to every possible arrangement of stars and gas. Tidal stripping creates another route. A small galaxy orbiting a larger one can lose its outer stars and gas through repeated gravitational encounters. The remnant may become compact, distorted, or extremely faint. If it once had a black hole, that black hole might remain as the dense center of a stripped nucleus. In some cases, compact stellar systems may be the surviving cause of the larger galaxies, and a central black hole inside them would be a relic of that past. But stripping can also remove gas before a black hole grows, or leave behind a stellar body whose original center is no longer obvious. Interactions can both reveal and erase. They can create unusual systems where the presence or absence of a black hole depends on the sequence of loss. A galaxy may be reduced to a remnant that still carries its dark center, or to one that never had enough time to grow one. Then there are galaxies shaped mainly by environment. A satellite falling into a galaxy cluster can have its gas swept away by hot surrounding plasma. Without gas, star formation declines, and any central black hole loses fuel. A dwarf orbiting a massive galaxy can be stirred by tides until its original disk becomes a rounder spheroidal system. A galaxy in isolation may evolve slowly, keeping its gas and forming stars without major disruptions. Each setting changes the odds of building a black hole. Dense environments bring encounters, stripping, and mergers. Isolation brings calm but fewer strong inflows. Neither path guarantees one result. The center is a record of circumstances. This variety is why a confirmed black hole-free galaxy would not stand alone as a freak object. It would belong to a broader lesson already visible across galactic astronomy. Galaxies do not all grow the same way. Some become massive ellipticals through repeated mergers and almost certainly build central giants. Some become spirals with disks and moderate bulges, likely carrying black holes that feed only occasionally. Some remain bulgeless, diffuse, irregular, or stripped, with centers that may be ruled by star clusters. Gas clouds, or nothing especially compact. The black hole connection may strengthen with mass and central density, then fade into uncertainty among the faintest systems. The universe may not draw a sharp line, it may draw a gradient. At one end, the central black hole is expected. At the other, it is optional. Galaxies that grow differently make the original question calmer and more precise. A galaxy without a black hole is not a violation of the idea of a galaxy. It is a possible result of a particular developmental path: low central density, weak inflow, shallow gravity, lost gas, limited mergers, or early disruption. It may not be common among great luminous galaxies, but it may be natural among small or diffuse ones. The absence would not make the galaxy less real. It would make its history different, in the stillness of a bulgeless disk, in the faint spread of an ultra-diffuse system, or in the uneven glow of an irregular dwarf. The universe shows that a centre does not have to become an abyss. Sometimes matter gathers into stars and never takes the final compact step. Sometimes the galaxy grows wide instead of deep. Sometimes the hidden architecture is enough. A confirmed galaxy without a central black hole would be quiet at first glance, but its meaning would be loud. It would not overturn the basic definition of a galaxy, because a galaxy is already understood as a bound system of stars, gas, dust, remnants, and dark matter. It would not make spiral arms impossible, or dissolve the outer halo, or erase the long orbits of old stars. Instead, its importance would come from the broken expectation at the centre. For decades, black holes and galaxies have appeared to grow in the same broad story. Massive galaxies often contain massive central black holes. The black hole mass tends to echo the properties of the surrounding bulge. Active galactic nuclei show that black holes can shape gas, regulate star formation, and throw energy across their hosts. A galaxy with no central black hole would not deny any of that. It would mark the boundary of it. It would show where a powerful pattern stops being a rule. The first consequence would be a clearer separation between galactic formation and black hole formation. If even one well-studied galaxy, with strong limits and resolved central motions, could be shown to lack a central black hole of meaningful mass, then the galaxy itself would become proof that stars and dark matter can assemble into a lasting system without that compact endpoint. It would turn possibility into example. The galaxy would become a natural laboratory, not for what a black hole does, but for what a galaxy can do without one. Its star formation history, central density, gas content, and dark matter structure would be examined for clues. Did it never form a seed? Did it lose one? Did its gas remain too turbulent, too thin, or too easily expelled? Did it avoid the mergers that build dense bulges and feed central objects? Every feature would become part of the missing black hole's biography, a biography written by absence. A confirmed absence would also change the way astronomers read correlations. The relationships between black holes and galaxy bulges are often treated as signs of coevolution. The black hole grows while the bulge grows, and each affects the other through gravity, gas supply, and feedback. But a black hole-free galaxy would remind science that correlations can have exceptions that reveal the underlying mechanism. If the galaxy has no bulge, the absence may show that bulge growth and black hole growth are linked through inward gas flow. If the galaxy has a bulge but no black hole, the result would be more surprising, suggesting that a dense central stellar structure can form without successfully creating or retaining a central compact object. If the galaxy is a dwarf, its absence may point toward a mass threshold. If it is large, the consequences would be more dramatic, forcing a closer look at how often black holes are ejected, hidden, or unnecessary even in mature systems. The absence would sharpen the seed problem. Every central giant begins somewhere, and a galaxy without one would constrain the ways those beginnings happen. If black hole seeds are expected from the deaths of the first massive stars, then why did this galaxy not preserve one in its centre? If direct collapse creates heavy seeds only in rare environments, then perhaps this galaxy never met those conditions. If dense clusters build intermediate seeds, perhaps its early clusters were too loose, too short-lived, or disrupted too quickly. A black hole-free galaxy would therefore become evidence about the early universe, even if the galaxy is observed nearby. Its present centre would be a fossil of conditions long gone. The missing object would say something about primordial gas, star formation, feedback, and the first dark remnants. Feedback theories would also be tested. In massive galaxies, black holes are often invoked to explain why star formation slows or stops. A feeding black hole can heat gas, drive winds, and prevent cooling. If a galaxy lacks a central black hole, then its history of star formation must be explained through other processes. Perhaps supernovae regulate the gas. Perhaps environmental stripping removes it. Perhaps the galaxy's halo is too small or too hot to allow steady cooling. Perhaps star formation declines simply because the fuel runs out. Such a galaxy would help separate black hole feedback from stellar feedback and environmental effects. It would reveal which parts of galactic aging require a central engine and which can happen through ordinary stars and surrounding conditions. A confirmed absence would change the search strategy for future surveys. The census would become two-sided. Detections would map the growth of black holes. Non-detections, when strong enough, would map the gaps. These gaps might cluster in low-mass galaxies, diffuse galaxies, stripped satellites, or systems with unusual merger histories. They might reveal a gradual decline in black hole occupation towards smaller masses, or they might reveal a more complex pattern, where some tiny galaxies contain black holes while some larger diffuse galaxies do not. The result would make black hole occupation a property to be measured, not assumed. It would become part of a galaxy's identity, not as a label of success or failure, but as one more trace of how matter entered, cooled, settled, and sometimes escaped. Black holes are so extreme that they can dominate the imagination. They seem like final answers, places where gravity reaches its hardest edge and ordinary intuition fails. Yet a black hole-free galaxy would restore attention to the less dramatic forces that do most of the building. Dark matter gathers the first wells, gas cools and fragments, stars form, age, enrich the medium, and die. Supernovae stir the interstellar matter, tides reshape systems, mergers rearrange orbits, long before a central black hole becomes visible. The galaxy is already a living gravitational structure. The absence would remind astronomy that the most spectacular object in a system is not always the most necessary one. The universe can build with quiet ingredients. It can make an island of stars without placing a horizon at its middle. A single confirmed case would not mean that black holes are unimportant. It would not erase quasars, jets, accretion disks, or the central mass of the Milky Way. It would not weaken the evidence that many large galaxies carry supermassive black holes. Instead, it would refine the story. The question would become conditional. Under what circumstances does a galaxy grow a central black hole? Under what circumstances does it fail? How does that answer depend on mass, environment, age, and structure? Science often advances this way, not by replacing a pattern with chaos, but by discovering the boundary that explains why the pattern exists. A black hole-free galaxy would be one of those boundaries. It would turn an assumption into a map. The most powerful outcome would be the recognition that absence itself can be a form of evidence. Astronomy usually celebrates bright detections, a flare, a jet, a fast orbit, a gravitational wave, a luminous quasar. But some truths are found by narrowing what cannot be there. A carefully measured empty centre would be a negative discovery with positive meaning. It would say that the galaxy's centre has been weighed, watched, and tested, and that no central black hole is needed to explain it. That kind of absence is not a blank. It is a constraint on the universe. It is the shape left when an expected object fails to appear. If such a galaxy is found with confidence, the question would not end. It would become more precise and more interesting. how many others are like it? Are they relics of early failure, survivors of ejection, or products of gentle histories? Do they live mostly in the faint outskirts of galaxy populations? Or are there larger examples hiding behind old assumptions? What happens to a galaxy when its centre is ruled by stars alone? The confirmed absence of one black hole would open the possibility of a whole class of galaxies whose histories diverge from the familiar path. The rule would bend, and in the bend the universe would become more varied. A galaxy without a black hole would not be less complete. It would be complete in another way, held by the gravity of the many rather than the darkness of one. Its meaning would rest in that quiet fact the centre of a galaxy can matter deeply. But it does not always have to be an abyss. The dark question remains because galaxies are not simple machines with one missing part. Their history is held together by gravity, and a history can lead to more than one kind of centre. In some galaxies, the centre becomes an engine. Gas falls inward, brightens, and announces a black hole whose mass has grown through time. In others, the centre becomes a quiet cluster of old stars, dense but ordinary, moving through a shared gravitational field with no need for a compact horizon. Between these possibilities lies the uncertainty that makes the question so persistent. A galaxy may need dark matter to form its broad well. It may need gas to cool and stars to ignite. It may need enough mass to resist being scattered apart. But it does not obviously need a central black hole in order to be a galaxy. The black hole belongs to a later layer of the story, a powerful layer, often present, often influential, but still not identical with the galaxy itself. This distinction is easy to lose because black holes carry such deep symbolic weight. They seem final. They mark the place where known physics approaches its sharpest boundary, where event horizons separate what can return from what cannot, where matter and information raise questions that reach beyond ordinary astronomy. A supermassive black hole at a galactic centre feels like the ultimate source of order because it is the most extreme object there. Yet extremity is not the same as necessity. The most compact mass in a galaxy is not always the mass that governs the whole. The outer stars, the halo, the gas streams, and the satellite systems follow the wider distribution of matter. A galaxy is a city of gravity, not a monument balanced on a single dark stone. If the stone is absent, the city may still stand, though its centre has a different story to tell. The strongest answer may therefore be layered. Could a galaxy exist without a black hole in principle? Yes, gravity allows it. Structure allows it. Galaxy formation does not require an event horizon at the beginning. Could many large galaxies exist without one that is less likely? Because massive galaxies provide repeated chances for black hole seeds to form, sink, merge, and feed. Their deep centres act as traps for compact remnants and inflowing gas. Their merger histories increase the odds that any missing seed is replaced by another. In those systems, a central black hole may be so common that its absence would demand explanation. But could some galaxies, especially small, diffuse, or disrupted ones, remain without a central black hole of meaningful mass? That possibility remains open and perhaps expected at the margins. The universe often makes rules that soften into probabilities when examined closely. The boundary is not a clean line. It may be an occupation fraction, a changing chance that a galaxy hosts a central black hole depending on its mass and history. Near the high end, the fraction may approach certainty. Near the low end, it may fall. Some dwarf galaxies may contain ancient seeds. Some may contain none. Some may have lost theirs. Some may hold black holes that wander rather than sit at the centre. The census is still incomplete because the faintest centres are the hardest to measure and the smallest black holes are the easiest to hide. This means the dark question remains partly observational. The universe may already contain the answer in thousands of quiet galaxies, but the evidence is written in motions too small, signals too faint, and centers too distant to read with confidence. Future instruments may change the shape of the silence. Sharper views of nearby dwarf galaxies can map the motions of stars near their centers. Deeper surveys can search for weak active nuclei and rare flares from dormant black holes. Radio arrays can look for compact sources that visible light misses. Each improvement will turn some candidates into detections and others into stronger absences. The result may not be a single dramatic discovery, but a slow tightening of the map. Some galaxies now thought to be empty will reveal hidden centers. Some now uncertain will remain quiet under every test. In that gradual sorting, astronomy will learn not only where black holes are, but where they are not. A confirmed empty center would not diminish black holes. It would make them more precise. Their importance would become conditional rather than assumed. They would appear as outcomes of certain histories, not automatic features of all galactic systems. This would also help explain why black holes and bulges so often seem connected. Perhaps the connection is not written into the definition of a galaxy, but into the processes that build dense centers, gas inflow, mergers, nuclear star clusters, and repeated feeding episodes create both bulges and black holes. Where those processes are weak or absent, the connection fades. A galaxy without a black hole would then be a quiet control case, a natural experiment showing what happens when stars and gas evolve without the regulating presence of a central compact engine. It would show how much of galactic life can be explained by ordinary feedback, environment, dark matter, and time. There is also a philosophical restraint inside the question. Absence is difficult to prove, and astronomy is often a science of inference. A black hole is not seen directly by ordinary light. It is weighed through its influence. When that influence is not detected, the honest answer is not immediate certainty, but a narrowing range of possibilities. The center may be empty of any significant black hole, or it may contain one below current limits. It may be empty now, or it may have lost a black hole long ago. It may not have a central black hole, while still containing many stellar remnants elsewhere. The universe resists simple categories. Even the phrase without a black hole carries layers without a supermassive black hole. Without any central black hole, without any black hole at all, or without one that matters dynamically. Each version opens a different door. The calmest answer is that galaxies can be understood without making a central black hole the defining feature. Black holes are woven into the story of many galaxies, but they are not the loom on which every galaxy is made. The loom is gravity acting across scales, dark matter gathering halos, gas cooling into stars, stars enriching gas, and time allowing structure to deepen or fade. The black hole, when it appears, is one of the most astonishing products of that process. It can feed, flare, regulate, and merge. It can bend the fate of gas and mark the nucleus with darkness. But a galaxy may still be a galaxy if the process never makes that final compact object at the center. It may be faint, small, diffuse, stripped, or simply quiet. Its existence would not shout, it would persist. This is what makes the question beautiful rather than merely technical. It asks whether the universe builds by necessity or by tendency. Some structures seem required. Gravity must gather matter. Stars need dense gas. Heavy elements need earlier generations of stars. But central black holes may belong to a different category, common consequences that emerge when enough paths converge. In the largest galaxies, convergence is strong. In the smallest, it may fail. The difference turns the cosmos from a rigid design into a landscape of outcomes. A galaxy without a black hole would not be an exception that breaks the universe. It would be one valley in that landscape, a place where matter found another route through time. The dark question remains because the answer is hidden in quiet centers, and quiet centers do not hurry to speak. Some are silent because an unfed black hole waits there. Some are silent because the black hole is too small. Some are silent because the black hole has wandered away. Some may be silent because the expected darkness was never born. Each possibility is scientifically meaningful. Each points to a different past. As telescopes improve and surveys deepen, the boundary between silence and absence will become sharper. Though perhaps never perfectly sharp, the mystery will thin, galaxy by galaxy, center by center, until the pattern becomes clear enough to trust. For now, the most careful conclusion is also the most open one. A galaxy can exist without being ruled by a black hole. It may even exist without a central black hole at all. What remains uncertain is how often nature chooses that path, and what kind of histories leave a galaxy with stars at its heart instead of an event horizon. The darkness at the center of a galaxy may be an object, or it may be only the limit of what has been found. In that uncertainty, the galaxy remains itself, a slow island of matter held not by one hidden point, but by the immense and patient gravity of the whole. The question settles into a quieter form. A galaxy does not become less real because its center may lack a black hole. It remains a gathering of stars, gas, remnants, dust, and unseen matter, moving through a gravitational field written across its whole body. Some galaxies carry a central darkness that feeds, flares, and reshapes the gas around it. Others may carry only a sleeping mass, too still to reveal. And some, perhaps in the faintest margins of the cosmic population, may carry no central black hole at all. Their centers may be filled with old stars, thin gas, or a compact cluster that shines softly where an event horizon might have been expected. The universe allows such variety because galaxies are histories, not single commands. They grow from chance densities, cooling clouds, collisions, losses, and long silences. A black hole may be planted early, delivered by merger, built by inward flow, starved into invisibility, kicked away, or never formed. Each path leaves a different kind of center. The mystery remains because darkness has more than one meaning. It can be the shadow of an object, or the absence of one. It can hide a giant, or mark a place where gravity never made that final descent. As instruments sharpen and faint galaxies yield their motions, the silence will become easier to read, though perhaps never completely simple. For now, the open answer is enough. A galaxy can be held by the gravity of the whole. Its stars can continue their slow orbits without a single abyss beneath them. Somewhere in the deep sky, there may be a quiet island of light whose heart is not a black hole, but only stars moving patiently through time.